This is a joint work with Riccardo Colini-Baldeschi from Meta Research and Sophie Klumper and Guido Schäfer from CWI and the University of Amsterdam, and Sophie is there. So this is about a certain mechanism design problem without money, but in the learning augmented paradigm, or with the line of work, which is called mechanism design with prediction. So let me give you just something more general, a bit more briefly. So we have, in the classical approximation algorithm perspective, we have a gamma approximation algorithm, being an algorithm which, for each instance, outputs a guarantee of the form on this box on the right. So if this happens, then we can say that in the worst case, this is a gamma approximation algorithm in whichever setting you have. Now, going beyond worst case analysis is something that people in the area have been considering in many different ways. One paradigm which is particularly interesting is what is called algorithms with predictions. Now, in this world, you have an instance, but it is in some sense augmented with a prediction. And the prediction can be something, some information about problem-related parameters. So it could be something that helps you do better algorithm, like in terms of what you're computing or what you're approximating. Now, in this environment, except approximation in the sense I defined before, in the worst case, we are also interested in studying the performance of a mechanism with respect to the benchmarks of consistency, which means the approximation achieved whenever this prediction is perfect. It is really useful to us. But then on the other hand, we also want to safeguard ourselves because this prediction can also be arbitrarily bad. And this is why this beyond worst case paradigm kind of retains this worst case flavor. So we want robustness if the prediction is bad. And you can also have a smooth interpolation between the two by defining an appropriate error notion. So this is quite popular in the area of online algorithms. There is a very rich line of work. And more recently, by the two papers on the slide, it has been proposed that we should be studying also problem strategic environments or mechanism design setting. Now, about our model. So let me first talk about our problem without predictions, and then tell you how predictions come into play. Now, in general, as the title said, we study assignment mechanisms. And when I say assignment mechanisms, we study a model which is basically the generalized assignment problem. But for the purpose of the talk, I will only focus on a special case, the case of weighted bipartite match. Now, imagine if you have a bipartite graph and the nodes on the left represent strategic agents, while the nodes on the right represent resources. And in this graph, you have an edge whenever the agent on the left wants to be matched to a resource on the right. So an edge is a declaration of a compatibility of an agent to a resource. Now, the values on these edges show how much this agent wants to be matched to this resource. Now, this is kind of crucial. These values are public information. These are not private, okay? But what is private is the edge set of each agent I. So each agent I has a set of edges EI, which are the true resources with which this agent is compatible with. And since this agent is strategic, they may report it, but they also may strategize about it and report a slightly different edge set in order to do better. And I will tell you in a bit what that means. Now, our goal is to design strategy-proof mechanisms, the goals for this problem, that compute a maximum weighted matching, which is a mechanism of just the declarations, or something which is as close to it as possible. Okay? And when I say maximum weighted matching, I mean a matching of total maximum value here. So this model was proposed by Dugmi and Ghosh, and it is called the private graph model. Now, recall this is a problem without money. So the utility here is just a function of the declarations, which is, for an agent I, it is Vij if the mechanism has assigned agent I to a resource J, which is in their true edge set. So if this is something they really want, they value it. But if the mechanism decides to assign them to something they don't want, their utility is just 0. Okay. And strategy proofness here means that it should be a weakly dominant strategy to declare the true edge set. Now, you may think, okay, this is just weighted bipartite matching. I can solve this in polynomial time. Well, the thing is, any optimal algorithm is not, in fact, a strategy-proof mechanism in this environment. Consider the graph on the left. The maximum weighted matching here is to get the 2 parallel edges. But then suppose that agent 1, which is the first agent on the left side, the first node on the left side, decides to hide edge 1A. Then the maximum weighted matching becomes just the cross edge 1B. And therefore, what happened here is that the optimal algorithm was assigning agent 1 a value of 2, but now that agent 1 pretends that they don't want resource A, they suddenly get a value of 3. So they improve by lying, and therefore the optimal solution, the optimal algorithm cannot guarantee strategy proofness in this setting. Well, in fact, there is a lower bound of 2 for this problem without predictions. And this was also shown by Dugmi and Ghosh. So a 2 approximation is the best possible strategy proof mechanism can achieve. And well, the algorithm for that is quite simple. It is just a very natural greedy algorithm which sorts the edges in their value in a non-increasing way, and just greedily assigns edges while making sure that the edge set constructed remains a match. So this very simple algorithm is a 2 approximation, or very important why it is a 2 approximation, and this is the best possible. Now we have predictions, and the goal would be for us to do better than this 2 approximation. And suppose that except for all the input, we also have access to a predicted matching, which is could be a subgraph of the complete graph. So what I mean by that is that it does not really depend on declarations. It could be just a matching which is like has no overlap with the declaration if it's bad. It could also be the optimal valid one. So that would help us. And so our prediction error is defined by eta. It's a number between 0 and 1. And it is natural in the sense that in its extremes also, if eta is 0, then it means that the value of the matching, if you take the overlap with the declarations, is exactly the value of the optimal match. And then if eta is 1 here, you may have that the prediction is completely erroneous. Now, let me start with the first very naive mechanism with predictions. And this is a mechanism called trust. And the only thing this mechanism does is that it just consults what the prediction says and just takes the intersection with the declared edges. Now, this mechanism, if we were just looking into approximation in terms of our eta parameter, is a 1/1 minus eta approximation mechanism. It is GSP. This is group strategy proofness. In fact, it is anything you want it to be in terms of incentives because it's super trivial. basically ignores the private input. Well, its problem is that if the prediction is perfect, so if eta is 0, this is even the optimal mechanism. But of course, eta can also be 1 or close to 1, in which case this mechanism doesn't give us any tangible robustness guarantee. So that's its problem. So, but what can you expect? Well, we show the following consistency robustness trade-off for this problem. So we say that for a gamma parameter which is greater or equal to 1, so there cannot be a deterministic strategy proof mechanism which is 1 plus 1 over gamma consistent, and at the same time 1 plus gamma minus epsilon robust. So what we mean here is that if you really want to do better than the 2 approximation, so for example, set gamma to be 2, so you get a 3 over 2 consistency, so which is already better than the 2 of Dugmin-Gauss, you have to settle for a mechanism which is 3 robust. So you cannot expect for a better robustness than that. And in this talk, I will show you what is a mechanism that achieves this consistency robustness trade-off. Now, to get some intuition on how we design such a mechanism, we have essentially a conflict here. We have two mechanisms. One of them is entirely consistent and not robust at all, which is trust. And the other one is robust, but it does not consult the prediction in any way, because this would violate the greedy order. And one thing we definitely know is that we want to keep the value-based ordering of edges of agents, because otherwise we will probably not get truthfulness. But at the same time, we really want to give some priority to predicted edges so that we do better when the prediction is good. Now, the solution to this dilemma is to design a deferred acceptance algorithm. So the way it works is that we essentially reduce our private graph model to the world of Gale-Shapley, in the sense that we define a preference order for the agents and a preference order for the resources, and we design it in a way so that agents propose to resources. Now, the proposal order for agents, we cannot really be creative, as I said before. We really need to respect their value-based ordering, so it will just be the resources ordered by their true value. Now, for resources, what we do here, we basically exploit the fact that the resources are not strategic, agents are. And we instead design their preferences by their boosted values. And a boosted value theta ij for an edge I comma j is just a value if this edge is not predicted. But if it is predicted, we boost it. So its value is gamma times beta ij. So this gamma, as it increases, it gives a higher value to the predicted edges. And now, the way this mechanism works is that it starts with an empty edge set. It constructs the preference orders of the agents, and then, depending on the rule on while there exists an active agents, and our framework is quite general in how can this be done. So an active agent is chosen, and the agent I proposes to resource J, and we say that they propose a theta I comma j, which theta is the boosted value, even though the order of their proposals is done by their value. This is very crucial, that each agent does proposals in order of their true value, but proposes a boosted value to the resource. And then the resource may accept if this match is better than what they already have, in which case then the proposal is done and the next round goes. Now, this mechanism is group strategy proof. It is 1 plus 1 over gamma consistent and 1 plus gamma robust. So we do match the consistency robustness trade-off lower bound I show you. And the intuition here is that if gamma is equal to 1, basically this is just the 2 approximation mechanism. It's almost outcome equivalent to the greedy mechanism of Dugmin-Gauss. And if you set gamma to be infinity, if you look at the consistency expression here, it will be 1, but robustness will be infinite. So it really is the middle ground between the two. Now, group strategy proofness works because we have basically reduced this to a deferred acceptance mechanism. Okay? And we have stability in the end. The resulting matching is a stable matching. And consistency robustness analysis works by basically generalizing a simple charging argument and observing that in a bipartite matching, in the worst case, an edge can block 2 optimal edges. So you generalize this through gamma. Now, for randomized mechanisms, if we are allowed to randomize, we can do strictly better than the deterministic lower bound. So what you should do here is you can, if you are allowed to compose boost and trust also in a randomized way, then you can get a strictly better robustness for the same consistency. And so weighted bipartite matching is just a special case of the generalized assignment problem. So you can still represent it with a bipartite graph. And now edges, except of having a value, they also have a size, and resources have a certain capacity, and you need to respect the capacity constraints of the resources. Well, weighted bipartite matching is just one special case. Knapsack is another. Multiple knapsacks are another. So there's like a family of combinatorial optimization problems which are special cases here. And you can keep the same perspective here. This private graph model of Dugme and Ghosh says to us that the edges on the left are strategic and they want to just be assigned to resources. Now, there is like an entire family of problems here, which you can look at this graph, and we study, like we extend some of the techniques that I showed you before, either using greedy algorithms or deferred acceptance auction or combinations of them, in order to get deterministic and randomized group strategy proof mechanism. Whenever we have randomized mechanism, we get universally group strategy mechanisms. And whenever you don't trust the prediction, we do retrieve the state of the art in the literature without prediction. So this is all I had to say. Thank you for your attention.